Hello everyone, I'm Madam Sheila and today we'll be learning about chapter 3, which is processes. This is an outline of what we'll be learning today. We have process concept, process scheduling, operations on processes, inter-process communication, IPC in shared memory systems, IPC in message passing systems, examples of IPC systems, and communication in client-server systems. So here are the objectives that we're trying to achieve by the end of the chapter. It is to identify the separate components of a process and illustrate how they are represented and scheduled in an operating system. Second, to describe how processes are created and terminated in an operating system, including developing programs using the appropriate system calls that perform these operations. The third one is to describe and contrast inter-process communication using shared memory and message passing. The fourth one is to design programs that uses pipes and POSIX shared memory to perform inter-process communication. And the fifth one is to describe client-server communication using sockets and remote procedure calls. And the last one is to design kernel modules that interact with the Linux operating system. Process concept. An operating system executes a variety of programs that run as a process. Process is a program in execution. Process execution must progress in sequential fashion. There's no parallel execution of instructions of single process. Multi-parts. The program code is also called text section. Current activity including program counter, processor registers. Stack containing temporary data, function parameters, return addresses, local variables, data section containing global variables, and heap containing memory dynamically allocated during runtime. Program is passive entity stored on disk. Process is active. Program becomes process when an executable file is loaded into memory. Execution of programs started via GUI, mouse clicks, command line entry of its name, etc. One program can be several processes. It considers multiple users executing the same program. Process memory is divided into 4 sections as shown in figure below. The text section comprises the compiled program code read in from non-volatile storage when the program is launched. The data section stores global and static variables allocated and initialized prior to executing main. The heap is used for dynamic memory allocation and is managed via calls to new, delete, malloc, free, etc. The stack is used for local variables. Space on the stack is reserved for local variables when they are declared at function entrance or elsewhere, depending on the language. And the space is freed up when the variables go out of scope. Note that the stack is also used for function return values, and the exact mechanisms of stack management may be language specific. And this is a memory layout of a C program. As a process executes, it changes state. The state of a process is defined in part by the current activity of that process. Each process may be in one of the following states. New, the process is being created. Running, instructions are being executed. Waiting, the process is waiting for some event to occur, such as an input-output completion or reception of a signal. Ready, the process is waiting to be assigned to a processor. And terminated, the process has finished execution. And as you can see here, this is a diagram of process state. Process control block, also known as PCB. Each process is represented in the operating system by a process control block, also called a task control block. It contains many pieces of information associated with a specific process, including these. Process state. The state may be new, ready, running, waiting, halted, and so on. Program counter. The counter indicates the address of the next instruction to be executed for this process. CPU registers. The registers vary in number and type depending on the computer architecture. They include accumulators, index registers, stack pointers, and general-purpose registers, plus any condition code information. Along with the program counter, this state information must be saved when an interrupt occurs to allow the process to be continued correctly afterward. Next, we have CPU scheduling information. This information includes a process priority, pointers to scheduling queues, and any other scheduling parameters. And we have memory management information. This information may include such information as the value of the base and limit registers, the page tables, or the segment tables, depending on the memory system used by the operating system. Accounting information. This information includes the amount of CPU in real time used, time limits, account members, job or process numbers, and so on. And then we have input-output status information. This information includes the list of input-output devices allocated to the process, a list of open files, and so on. In brief, the process control block simply serves as the repository for any information that may vary from process to process. The process model discussed so far has implied that a process is a program that performs a single thread of execution. Consider having multiple program counters per process. Multiple locations can execute at once, and multiple threads of control is called threads. And we must then have storage for thread details. Multiple program counters in process control block. And we're going to explore more of it in detail in chapter 4. This is a process representation in Linux. Process scheduling. Process scheduler selects among available processes for next execution on CPU core. And the goal is to maximize CPU use, quickly switch processes onto CPU core. It maintains scheduling queues of processes. Ready queue. Set of all processes residing in main memory, ready and waiting to execute. Wait queues. A set of processes waiting for an event, like input-output. And processes migrate among the various queues. This is how ready and wait queues look like. And this is a representation of process scheduling. The diagram below shows CPU switch from process to process. A context switch occurs when the CPU switches from one process to another. Context switch. When CPU switches to another process, the system must save the state of the old process and load the saved state for the new process via a context switch. Context of a process represented in the process control block. Context switch time is pure overhead. The system does no useful work while switching. The more complex the operating system and the process control block, the longer the context switch. Time dependent on hardware support. Some hardware provides multiple sets of registers per CPU, and multiple contexts are loaded at once. Multitasking in mobile systems. Some mobile systems, for example, early version of iOS, allow only one process to run. Others are suspended. Due to screen real estate, user interface limits iOS provides for a single foreground process controlled via user interface and multiple background processes in memory running but not on the display, and it has limits. Limits include single short task, receiving notification of events, specific long-running tasks like audio playback, and Android runs foreground and background with fewer limits. Background process uses a service to perform tasks. Service can keep running even if background process is suspended. Service has no user interface and it has small memory use. Operations on processes. System must provide mechanisms for process creation and process termination. Okay, for process creation, parent process create children processes, which in turn create other processes, forming a tree of processes, generally process identified and managed via a process identifier. Resource sharing options. Parent and children share all resources. Children share a subset of parents' resources. Parent and child share no resources. Execution options. Parent and children execute concurrently, and parent waits until children terminate. Address space. Child, duplicate of parent. Child has a program loaded into it. Unix examples. Fork system call creates new process. Exec system call used after fork to replace the process memory space with a new program. Parent process calls waiting for the child to terminate. This is a tree of processes in Linux. And C program forking separate process. This is how we can create a separate process via Windows API. Okay, so for process termination, process executes last statement and then asks the operating system to delete it using the exec system call. It returns status data from child to parent. Process resources are deallocated by operating system. Parent may terminate the execution of children processes using the abort system call. Some reasons for doing so are child has exceeded allocated resources and task assigned to child is no longer required, and the parent is exiting and the operating system does not allow a child to continue if its parent terminates. Some operating systems do not allow a child to exist if its parent has terminated. If a process terminates, then all its children must also be terminated. Cascading termination. All children, grandchildren, etc. are terminated. The termination is initiated by the operating system. The parent process may wait for termination of a child process by using the wait system call. The call returns status information in the PID of the terminated process. If no parent waiting did not invoke wait, process is a zombie. If parent terminated without invoking wait, process is an orphan. Android process importance hierarchy. Mobile operating systems often have to terminate processes to reclaim system resources such as memory. From most to least important, foreground process, visible process, service process, background process, empty process. Android will begin terminating processes that are least important. So we have here multi-process architecture Chrome browser. Many web browsers ran a single process, and some still do. If one website causes trouble, an entire web browser can hang or crash. Google Chrome browser is multi-process with 3 different types of processes. Browser process manages user interface, disk, and network input-output. Render process renders web pages, deals with HTML and JavaScript. A new renderer created for each website opened. It runs in sandbox, restricting disk and network input-output, minimizing effect of security exploits, and plugin process for each type of plugin. Inter-process communication. Processes within a system may be independent or cooperating.
cooperating process can affect or be affected by other processes, including sharing data. Reasons for cooperating processes are information sharing, computation, speed up, modularity, convenience. Cooperating processes need inter-process communication, and there are two models of IPC, which is shared memory and message passing. We can see here communication models for shared memory and message passing. Producer-consumer problem. Paradigm for cooperating processes. Producer process produces information that is consumed by a consumer process. There are two variations. Unbounded buffer places no practical limit on the size of the buffer. Producer never waits, and consumer waits if there is no buffer to consume. Bounded buffer assumes that there is a fixed buffer size. Producer must wait if all buffers are full. Consumer waits if there is no buffer to consume. Inter-process communication, an area of memory shared among the processes that wish to communicate. The communication is under the control of the user's processes, not the operating system. Major issue is to provide a mechanism that will allow the user processes to synchronize their actions when they access shared memory. And synchronization is discussed in more depth in chapters 6 and 7. This is bounded buffer shared memory solution. This is producer process in shared memory. This is consumer process in shared memory. Well, what about filling all the buffers? Suppose that we wanted to provide a solution to the consumer-producer problem that fills all the buffers. We can do so by having an integer counter that keeps track of the number of full buffers. Initially, counter is set to 0, and the integer counter is incremented by the producer after it produces a new buffer. And the integer counter is decremented by the consumer after it consumes a buffer. Okay, why was there no race condition in the first solution, where at most n1 buffers can be filled? We're going to cover that in chapter 6. Inter-process communication message passing. Processes communicate with each other without resorting to shared variables. IPC facility provides two operations: send message, receive message. The message size is either fixed or variable. If processes P and Q wish to communicate, they need to establish a communication link between them and exchange messages via send or receive. Implementation issues. How are links established? Can a link be associated with more than two processes? How many links can there be between every pair of communicating processes? What is the capacity of a link? Is the size of a message that the link can accommodate fixed or variable? Is a link unidirectional or bidirectional? Implementation of communication link for physical shared memory, hardware bus network for logical, direct or indirect, synchronous or asynchronous, and automatic or explicit buffering. Direct communication. Processes must name each other explicitly, like send P message, which is sending a message to process P, and then receive Q message, which is to receive a message from process Q. First, properties of communication link. Links are established automatically. A link is associated with exactly one pair of communicating processes. Between each pair, there exists exactly one link. The link may be unidirectional, but is usually bidirectional. Operations: create a new mailbox, port, and send and receive messages through mailbox, and delete a mailbox. Primitives are defined as send a message, which is to send a message to mailbox A, and receive a message from mailbox A. Mailbox sharing. P1, P2, and P3 share mailbox A. P1 sends, P2 and P3 receive. So who gets the message? Solutions: allow a link to be associated with at most two processes. Allow only one process at a time to execute a receive operation, and allow the system to select arbitrarily the receiver. Sender is notified who the receiver is. Synchronization. Message passing may be either blocking or non-blocking. Blocking is considered synchronous. Blocking send. The sender is blocked until the message is received. Blocking receive. The receiver is blocked until a message is available. And non-blocking is considered asynchronous. Non-blocking send. The sender sends the message and continue. Non-blocking receive. The receiver receives a valid message or null message. Different combinations are possible. If both send and receive are blocking, we have a rendezvous. Producer-consumer message passing. This is what it looks like for producer and consumer. Buffering. Queue of messages attached to the link. It is implemented in one of three ways. Zero capacity. No messages are queued on a link, and sender must wait for receiver. Rendezvous. Bounded capacity. Finite length of n messages. Sender must wait if link is full. And unbounded capacity. Infinite length. Sender never waits. Okay, so these are the examples of inter-process communication systems, POSIX. POSIX shared memory. Process first creates a shared memory segment, also used to open an existing segment. And it sets the size of the object. Use mmap to memory map a file pointer to the shared memory object. Reading and writing to shared memory is done by using the pointer returned by mmap. So this is what it looks like for inter-process communication POSIX producer. And this is what inter-process POSIX consumer looks like. So here are the examples of inter-process communication systems, MOC. MOC communication is message-based. Even system calls are messages. Each task gets to port at creation, kernel, and notify. Messages are sent and received using the MOC message function, and ports are needed for communication and are created via MOC, port allocate, and send and receive are flexible. For example, four options if mailbox is full. To wait indefinitely, wait at most n milliseconds, return immediately, and temporarily cache a message. Okay, so this is the MOC messages and MOC message passing for client. This is MOC message passing for server. So here are the examples of inter-process communication systems for Windows. Message passing centric via advanced local procedure call facility. Only works between processes on the same system, and it uses ports like mailboxes to establish and maintain communication channels. Communication works as follows. The client opens a handle to the subsystem's connection port object, and then the client sends a connection request. The server creates two private communication ports and returns the handle to one of them to the client. And the client and server use the corresponding port handle to send messages or callbacks and to listen for replies. This is the local procedure calls in Windows. Pipes. It acts as a conduit, allowing two processes to communicate. The issues are: is communication unidirectional or bidirectional? In the case of two-way communication, is it half or full duplex? Must there exist a relationship, for example, parent-child, between the communicating processes? Can the pipes be used over a network? Ordinary pipes. It cannot be accessed from outside the process that created it. Typically, a parent process creates a pipe and uses it to communicate with a child process that it created. Named pipes can be accessed without a parent-child relationship. Ordinary pipes. Ordinary pipes allow communication in standard producer-consumer style. Producer writes to one end, the right end of the pipe. Consumer reads from the other end, the red end of the pipe, and ordinary pipes are therefore unidirectional. It requires parent-child relationship between communicating processes. And Windows calls this anonymous pipes. Named pipes are more powerful than ordinary pipes. Communication is bidirectional. No parent-child relationship is necessary between the communicating processes. Several processes can use the named pipe for communication. It is provided on both Unix and Windows systems. There are two communications in client-server systems, which are sockets and remote procedure calls. A socket is defined as an endpoint for communication, concatenation of IP address and port, a number included at start of message packet to differentiate network services on a host. Communication consists between a pair of sockets. All ports below 1024 are well known. It's used for standard services and special IP address 127.0.1 loopback to refer to system on which process is running. This is what socket communication looks like. For sockets in Java, there are three types of sockets: connection-oriented, connectionless, and multicast socket class. Data can be sent to multiple recipients. Consider the state server in Java. This is the equivalent date client. Remote procedure call abstracts procedure calls between processes on networked systems. Again, uses ports for service differentiation. And stubs, client-side proxy for the actual procedure on the server. The client-side stub allocates the server and marshals the parameters. The server-side stub receives this message, unpacks the marshaled parameters, and performs the procedure on the server. On Windows, stub code compile from specification written in Microsoft Interface Definition Language. Data representation handled via external data representation format to account for different architectures, big endian and little endian. Remote communication has more failure scenarios than local. Messages can be delivered exactly once rather than at most once. Operating system typically provides a rendezvous or matchmaker service to connect client and server. And this is the execution of RPC. So that's all for chapter 3, and if you don't understand any of the things that I explained, you can ask me again in class or text me so I can explain it in more details to you guys. Bye!